I'm going to demonstrate an Excel-based shaft sinking schedule and control system that was specifically designed for a multi-billion-dollar mine development project. Shaft sinking is a cyclic process and it goes through phases: drilling the shaft bottom, charging the holes with explosives, blasting, re-entering the shaft, lining it with concrete, mucking, ground support, and installing services such as air, water, etc. Then repeating the cycle, but with variations in the activity sequence, blast depth, etc., depending on the conditions. The cycle could follow a 4.5 meter blast round that consists of two sub-cycles, the blue curb cycle and the brown services cycle, which together cover all the phases. The sub-cycles automatically switch over from one to the other each time the process passes through the re-entry phase. Because shaft conditions vary as sinking progresses, the project may need more than just the 4.5 meter cycle to accommodate those changing conditions. For example, there could be an alternative cycle based on a 3 meter blast round, made up of 3 shorter subcycles: the light blue curb cycle, the purple barrel cycle, and the orange services cycle. With that in mind, let's go to the Start of Shift tab to start scheduling. To begin, the macro clears the input cells and we enter the shift start parameters in the yellow cells. Date, 17 June. Shift, day shift. Blast round, 54. Subcycle, services cycle. We enter the primary start activity from the drop-down. Say, line up barrel plates, install concrete tubes. Activities are either successive, in other words, they are carried out one after another, or they are in parallel, i.e. they are done at the same time. The start activity here is successive, so there is no parallel activity. However, concreting and mucking are parallel activities. So if we choose concrete DEFG as the primary start activity, muck cycle 1 is automatically added as the parallel start activity. We enter the start quantities carried over from the previous shift. Let's say for concrete, 100 cubic meters. For muck cycle 1, 5 kibbles. Depth of shaft, 200. Previous services installation. Services are installed in either 1 or 2 6 meter lengths. Let's select 2. Previous advance, 4.5. Unlined shaft height, 17. Muck on bench in kibbles, 180. This cell converts kibbles to meters, 7.45 meters. Now, once these start parameters are done, all activities are automatically scheduled, showing durations, start time, end time. Activities scheduled for the upcoming shift are highlighted in dark gray. Activities with tangible outputs, such as kibbles and cubic meters, are tracked in units of production. These columns show required number of units for this shift. For muck cycle 2, it's 20.1 kibbles. This section describes the shaft at the end of each activity in terms of depth underground, unlined height, meters of muck on the bench with the equivalent quantity in kibbles. Safety and workability alerts warns us of issues and they must be resolved before the schedule can be implemented. There aren't any at this point, so the schedule is ready to go. This format of the schedule is very detailed, so let's go to the short interval control, which is easier to understand. The activities are on the left. The shift starts with the safety meeting and ends with muck cycle 2, 20.1 kibbles, before the crew goes to the surface at the end of the shift. The detailed plan is given, duration, time, and production. Let's go back to the Start of Shift tab. Shifts usually include activities other than just shaft sinking activities. For example, health and safety interventions, maintenance, etc. They have to be planned too. To plan a health and safety intervention, for example, say for after drill support, install mesh 1, we go to the activity override and select other. Give the description, health and safety intervention. Specify whether it's successive or in parallel, it's successive, and we give the duration, say 1 hour. If we go to the short interval control, we see here the health and safety intervention that's been added. It's good scheduling practice to look beyond just the upcoming shift. Shift look ahead indicates in how many shifts time the activities are scheduled for, and the light gray cells show when shift changes will occur. As we've seen, safety and workability alerts tells us when there are issues. It's best to address them now before they become bigger problems. So looking ahead, we have too much muck to scatter, 8.7, let's call that 9 kibbles. That means that we have to reduce the muck on the bench by that amount before we get to that activity. To do that, we can insert a mucking activity, let's say after the health and safety intervention. We go to the activity override drop-down, select mucking, and enter the quantity 9. The schedule gets pushed out by the time taken to muck 9 kibbles. We could deal with the 9 kibbles in a different way. We could add the 9 kibbles to an existing mucking activity. There are 3 to choose from. Muck cycles 1, 2, and 3. We choose the one with the most slack. Slack is created when activities are in parallel. It is an unscheduled capacity available to an activity, or said differently, the length of time the activity can be delayed before the schedule starts slipping. This column shows the slack. Muck cycle 1 has the most slack, 174 minutes. So let's delete the inserted activity and use the quantity override to add the 9 kibbles to the existing 5 of muck cycle 1. That gives us 14. That reduces the slack to 102 minutes, but now we are more efficient because we've added 9 kibbles of muck without increasing duration. Looking further ahead, there's a safety issue after the next blast. Unlined height exceeds 20 meters. We can solve that by changing the 4.5 meter blast to 3 meters using the quantity override. Notice that subsequent blasts remain 4.5 meters. Future blasts are easy to find. Just look for the red blast code. If we want to permanently switch to the 3 meter blast round, we do a manual subcycle switch. We go to the subcycle following the next re-entry and replace the 4.5 meter curb cycle with the 3 meter one using the activity override. Note that future blasts are now 3 meters. There might still be some future potential workability issues, but we don't need to look that far ahead right now. So the schedule is ready for execution. Once the schedule is done, the short interval control is copied by the Create Shift Control workbook macro and emailed to the crew. The purpose of the short interval control is, firstly, to monitor and control execution of the work, and secondly, to capture accurate production data. This is what the workbook looks like. It only takes a minute or two every hour to keep it updated. The yellow cells are the input cells. When the shift starts, the actual start time of the first activity is entered. Let's say it's 6:45. The first entry triggers the short interval control to forecast the remaining start times and end times in the black cells. At the end of each activity, the data capturer enters the end time and the start time of its successor. If the first activity ends at 7:15, the second runs from 7:15 to 7:20, and the next two are in parallel, so they both start at 7:20. The cumulative production numbers are updated hourly. For example, at 7:30, we update the two parallel activities, let's say 3 for concrete and 1 for mucking. Production variances are automatically shown in the row below the yellow cells, and the overall activity production rate on the right. We continue updating the production numbers hourly. At 8:30, 33 and 9 say. At 9:30, 65 and 12. At 10:30, 93 and 13. At 11:30, 115. Until the activities are completed and we enter the end times. 10:50 and 11:30. With each entry, the forecast, production rate, and variances are automatically updated. They give early warning if we're falling behind and allows us to take immediate corrective action before it becomes a bigger problem. Delays are recorded as well. Let's say there was a muck cycle 2 delay from 10 to 11. We enter the delay code 31.412 and the start time 10 o'clock and end time 11 o'clock. Delays are highlighted in blue automatically. At the end of the shift, the completed short interval control is emailed to the schedule administrator. Sometimes events during the shift require schedule updates or rescheduling whilst the shift is still in progress. If it's just a case of having fallen behind and we have to adjust the start times and end times, we use the schedule update mechanism. For example, drill support install mesh 1 was scheduled from 1:04 p.m. to 4:04 p.m. If it starts late, say 2 p.m., we enter the update time and go to the row of the activity and enter the quantity or percentage complete, which is 0, resulting in the end time being pushed out from 3:04 p.m. to 5 p.m. Likewise, if at 2 p.m. we're ahead, say 2/3 or 66.7% complete, the schedule end time is brought forward to 2:59 p.m. If the schedule requires more than just a time update, for example, a change in activity sequence or the addition of an activity, we use the reschedule mechanism. If, for example, at completion of concrete DEFG and muck cycle 1, there's a breakdown with the crew having to surface so that maintenance can go down and fix a problem, we'd have to add a maintenance activity and reschedule. To do that, we clear the input cells, enter the date, 17 June, and time, let's say 11:30. We enter the shift parameters and conditions. I've shown that before, so I'm fast forwarding that and going straight to scheduling the resumption of the shift. We select abnormal start from the activity override dropdown, call it maintenance, and let's assume it will take half an hour. The short interval control shows the revised schedule. The shift resumes at 11:30 with the crew returning underground half an hour later and surfacing at the end of the shift. Automated and structured reports are built into the system. They instantaneous and enable real-time decision making. To call out the reports, we select the end round, say 56, and specify the number of rounds per report period. Make it 1. The reports cover 3 areas: scheduling, execution, and delays. Starting with scheduling, there are 2 aspects. First, how well does the schedule use available project time? Before I go into that, I must explain the concept of earned duration and duration efficiency. If we have 3 critical path activities, A, B, C, requiring 3, 4, and 3 hours respectively, collectively the work will take 3 plus 4 plus 3 equals 10 hours. That's called earned duration. If we can do some of that work in parallel, let's say there's a 2-hour overlap between B and C, we could finish all 3 tasks in 8 instead of 10 hours of elapsed time. In other words, through better scheduling, we can do 10 hours of work in 8 hours. Duration efficiency equals earned duration divided by elapsed time, i.e. 10 divided by 8 equals 125%. Duration efficiency is an indicator of how efficiently scheduling uses available time. Now let's go to the report. There's a 12-period graph for each phase, one for switch, one for re-entry, one for concreting, etc. The blue bars are the earned duration. The overall hours work graph at the top of the report sums the earned durations for the phases. The green line is the duration efficiency measured on the right-hand side axis. The higher it is, the sooner the project will be completed. This duration efficiency graph has 2 peaks at rounds 50 and 55. The peaks were the results of the project team experimenting with parallel activities and hot seat shift changes. Every project should aim to maximize duration efficiency, but without sacrificing safety and quality. The second thing to look for in terms of scheduling is schedule accuracy and reliability. For some phases, we'd expect their earned durations to be about the same one round to the next. For example, if we look at mucking, the quantities are generally the same every round. Therefore, the blue bars are about equal in height and the peaks of the bars have a more or less flat pattern. For other phases, such as installing services, which only get done every second or third round, we'd expect a more up and down pattern. Let's look at installing services a little closer. Services are installed in 6-meter lengths. Therefore, to keep services installations in sync with the 4-meter blast round, we'd install 3 lengths every 4 rounds. 0 lengths in the first round, 1 in the second, 0 in the third, and 2 in the fourth. Let's say installing 2 lengths together is 25% more efficient than installing 1 separately. The arithmetic for that would show that the hours required for 4 rounds would be distributed 0 for the first round, 40% of the hours for the second, 0 for the third, and 60% for the fourth. The graph shows the expected earned duration for installing services. It goes up and down, but it repeats itself every 4 rounds. In other words, it's regular. If we go to the report, the expected earned duration is shown by the white bars. The blue bars are the actuals. For rounds 45 to 51, the actuals are irregular and do not match the expected earned duration. Inconsistent earned durations are probably due to the process, scheduling algorithm, and execution not being properly aligned. From round 52 onwards, the expected versus actuals improve once the alignment inconsistencies are eliminated. Getting schedule accuracy and reliability right early in the project minimizes delays in the future. The second reporting area is execution. How well do the crews carry out the work? Activities measured in tangible outputs such as kibbles and cubic meters can be analyzed and improved. Production rate analysis enables us to identify the factors of good performance and incorporate them into our syncing processes and eliminate the root causes of poor performance. Let's look at mucking. For rounds 45 to 56, the maximum production rate achieved for a round was 6.85 kibbles per hour with an average of 6, the black dotted line. The average and the maximum were both below the standard rate of 7.5, the red dotted line. However, the crew came close to the standard on a few occasions. Both night shift, the black line, and day shift, the blue line, have exceeded 7. We're only on blast 56, still early in the project, and the learning curve is steep, So by taking the right actions, we can raise the standard and improve performance going forward. By doing that, we set up the basis for continuous process improvement for the remainder of the project. The third reporting area deals with delays. The goal is to control the impact of delays and preserve available time. First, we must quantify the extent of the delays. The delay heat map helps us with that. The delay heat map is a matrix that plots where the delays are, re-entry, concrete, mucking, etc., and what the problems are, shaft plant and equipment, mobile plant and equipment, services, etc. Switch includes those activities not directly linked with sinking, for example, pre-start safety meetings, crew down to start shift, etc. We set the period for the delay heat map by giving the start and end rounds, let's say 45 and 56. The intersection of what the problem is and where the delay is displays the number of delays and the hours of delay. The brighter the red, the bigger the problem. The biggest problem for the period chosen is shaft, plant and equipment during mucking. The first graph ranks the problem areas: shaft, plant and equipment, regulatory and corporate, mobile plant and equipment, etc. The second graph ranks the phases in terms of the biggest time losses: mucking, switch, drilling, etc. The second step to managing delays is determining and dealing with the root causes. Let's go to root cause analysis level 1. The biggest problem is shaft, plant and equipment during mucking. So let's enter the phase mucking and the problem shaft, plant and equipment. The VSMs at 52% are the highest, followed by the winders at 42%. If we go to level 2 and select the biggest level 1 problem, i.e. VSMs, we see the biggest cause is hydraulic, which makes up 86% of VSM delays during mucking. Level 3 analyzes hydraulic further. All recorded VSM delays are from ruptured hoses. The next step is to take measures to eliminate or reduce the number of hose failures. Shaft sinking is a team sport. For it to succeed, there must be communication between the players. The project must ensure that the main sink contractor, engineering, geotech, HR, batch plant, blast contractor, procurement, maintenance, and all other materials and services suppliers are on the same page. If not, the result will be increased delays due to lack of coordination. To counter that, the system has automated project requirements forecasts, which provide suppliers with immediate up-to-date information. For example, to provide the batch plant with a concrete forecast, we select concrete, and the forecast indicates the look-ahead date and shift at the top on the left and specifies the next 20 orders in terms of concrete required, quantity, and delivery times. Similarly, if we wanted to check that the required material was in stock or in the pipeline for upcoming shaft services installations, we select Install Shaft Services, and the forecast lists the number of 6-meter lengths required and the dates and times. Forecasts are quick and easy. By keeping the suppliers informed, inefficiencies and delays are minimized. With that, we've covered the whole of the shaft sinking project management operating system. To sum up then, the shaft sinking schedule and control system comprises 4 integrated components: a short interval scheduling mechanism, short interval controls, automated structured reports, and a project requirements forecaster. A mentality of continuous process improvement runs through and connects all the elements of the system. And a final note, the system is built in Excel and therefore doesn't require additional investment in technology. Thank you for listening. If you want more information about scheduling and control systems, go to www.2globaleyes.com or email brent@2globaleyes.com.
2 Global Eyes. Use what you have. Don't spend what you don't need to. Do more with less.